In our last video, we started talking about the ambiguous case for law of sines, when I'm given two sides and an angle that's not in between them. What might happen in this case is I might have one triangle, or as we saw in the last video, we might have no triangles formed, or as we'll see in this video, there's actually going to be two potential triangles that are formed given this set of information. So I've started the problem the same way as I did last time by kind of sketching out what this might start to look like. I've got angle A drawn in here already. I've got side B figured out. And I need to compare my remaining side, that side A, to this straight up and down vertical edge right here. So to find that side, which I'm going to call H, I'm going to do B times the sine of A. That's just some simple trigonometry to find that H value. That would be the distance if I were to go straight down from the top, straight down to the bottom. So using a calculator and doing 16 times the sine of 40 degrees, I find that side H is approximately 10.3. And so what's going to happen in this situation, this is why I'm going to have two triangles. It turns out that side A is sort of in this sweet spot. It's longer than side H, okay? So I have enough distance to go straight down. It's going to actually be longer than that side. However, it's not quite as long as side B. It's shorter than side B. And so what happens, let me go back a screen real quick. We looked at this in a video in class. But what I have really is this third situation over here, where A is longer than H but shorter than B. So what can actually happen is two separate triangles could be drawn in this scenario. I could have a triangle that looks like this obtuse triangle, where things match up, or I could have this triangle formed over here, because again, A is in that sweet spot where it's longer than H but less than side B. And so I know right away that, okay, there are two triangles that are being formed. Let's go ahead now and take a look at how we'll solve for those triangles and figure out two separate sets of information for this situation. Alright, so now that I know there's two triangles that are going to be formed, we're going to go about using law of sines to find our two different sets of information. So I've started this problem by, you guys know I like to use the chart to solve these. So I've set up my chart with the sides and angles, and I've plugged in my given information. However, over here I've added this alternate angle B, and that's what we'll get to in a second, where I deal with the second set of information. Notice the givens are still the same. It's going to be where we find angle B that things start to take a different path. So I'll begin using law of sines, again, because I have this pair. I have a pair, an angle and a side that match up, so that's my cue for law of sines. And like I said, this part's going to be very familiar to you. So law of sines, I'm going to match up sine of angle 40 over side 13 would equal sine of angle B over 16. And so doing some cross multiplying and getting this worked out just like always, I'd have 13 times the sine of B is equal to about 10.28. I just used a calculator for that part. Dividing both sides by 13, then I get sine of B is equal to approximately 0.791. Remember, try to do as little rounding as possible. And then using my calculator to do the inverse sine of both sides, I'd find out that the inverse sine of 0.791 comes out to be, for angle B, approximately 52.3 degrees. I'm going to go ahead and add this number to my chart, 52.3 degrees. However, I'm going to note that that's where I'm going to need to go back to in a moment to find my alternate answer, because there's actually two angles that have a sine value of 0.791, going back and using some old trigonometry stuff. So we're going to come back to that in a second, but let's go ahead and finish figuring out what this first triangle is going to be. And so from here, again, same deal as always, as we've solved with law of sines before. My three angles in a triangle always need to add up to 180 degrees. So subtracting those angles from 180, I get 87.7 degrees for that missing angle. And finally, I just have one more thing to find in that side C. And so I think to do this, I'll do one more proportion. Again, same as always with law of sines. So I'm going to match up sine of 40 over 13 again. I'll use that again, angle A and side A. And this time I'm trying to find side C, so I'll match this up to the sine of 87.7 over side C. And so again, doing some cross multiplying, solving some proportions, I trust that you guys are able to do that part on your own. If not, go back and watch some of my old videos with law of sines. That missing side works out to be about 20.21 for that missing side. And again, just doing some simple checking, I can see that my biggest angle and biggest side still match up just like always. My shortest side, my smallest angle both match up as well. All right, so that's one triangle solved. And then nothing seems unusual. Everything worked out the same way it has always worked out. However, we've already said there's going to be two triangles this time because of that missing or that remaining side, side A, being in that sweet spot, being longer than this side H, but shorter than this B side. And so let's go ahead and talk about this alternate angle B. And so when we began, or a few minutes ago, I had said, remember this step right here because there's going to be a second answer we want to find. Recall that there are two quadrants where sine is positive. Sine is positive in quadrant 1 where all things are positive. However, sine is also positive in quadrant 2. And our calculator got us this acute angle in quadrant 1. However, we can go ahead and sketch this reference angle in quadrant 2 and find our alternate angle B. And so I'm going to go ahead and do that. So my reference angle is the angle we found. I'm going to go ahead and label that as 52.3 degrees. However, if I remeasure this and measure around this way, I find out by subtracting from 180, I find out that that angle is going to be 127.7 degrees, and that is going to be my alternate angle B. If you want to prove it to yourself to see that this actually does work, do the sine of 127.7, make sure you're in degree mode, and you'll see that that in fact does come out to also be approximately 0.791 positive. Okay, so that's how I find my alternate side or angle B. So let's go ahead and get that in the chart, 127.7 degrees, if I can squeeze that in there. And then from here it'll proceed hopefully just as you'd expect. Once again, my angles need to add up to 180 degrees. So subtracting those two angles from 180, I find out that my alternate angle C is going to be about 12.3 degrees. Often on this alternate triangle, you have one very obtuse angle and one very acute angle, as we do in this case. And then finally, to finish this, all I'm missing is side C. So I'm going to go ahead and do one more proportion. So sine of 40 over 13, matching up side A and angle A, would have to equal sine of 12.3. That's my alternate angle C, over side C. And so once again, doing some proportions, and I'll leave the math for you to do. I assume you can do that at this point. I find out that side C works out to be about 4.31. And again, just making sure that things match up, I can see that again, my shortest angle, shortest side. This time it's side C and angle C. Those match up. My biggest side and biggest angle also match up at angle B. And so that is how you'll find your two sets of information for these ambiguous case situations where you have two triangles that are formed. Hopefully you had a lot of fun. These problems are great, aren't they? Enjoy.